9.91 from week 9. So simple Brayton cycle. First thing popped to our mind is 2 isentropics, 2 isobarics, right? 1 isentropic compression, 1 isentropic expansion, 1 isobaric heat addition, 1 isobaric heat rejection. Using air, okay, so we can go to table A17, has a minimum and maximum cycle temperature of 27 and 727 Celsius. It's designed so that the maximum cycle pressure is 2,000, the minimum cycle is 100 kilopascals. Okay, theoretically there's only 2 pressures on the Brayton cycle, so this is going to be the maximum. Okay, that's going to be P2, P3. This is going to be P1, P4. Considering an isentropic efficiency of 80% of the compressor and 90% of the turbine, and a 50 kilopascal pressure drop across the combustion chamber, determine blah, blah, blah. So if there's a 50 kilopascal pressure drop on the combustion chamber, that means that our heat addition process, right, going from 2 to 3, is not going to be isobaric, right? So it's going to be a slight variation from the ideal Brayton cycle that we know. Determine the net power produced per unit mass, right? So the area inside of cycle, and the thermal efficiency. Use constant specific heats at room temperature, right? So if it's selling that, you guys need to highlight that to know the difference on whether we're accounting for the change or not accounting. In this case, we're doing the approximation, simplification, and not accounting for variation in specific heats, right? So we can use those relationships from P2, P1, T2, T1, or V1, V2, and so forth, right? Because our K, our CP, and our CV are going to be the same throughout the problem. So let's look at this minimum temperature, maximum temperature, and these pressures here. If you guys recall, I'm actually going to pull up this one again. If you guys recall the TS diagram on the Brayton cycle, it's probably the easiest way to see where the minimum temperature is and the maximum temperature is, right? Well, it's also intuitive, right? Because after you have your heat rejection, that's when you have the least amount of energy, so that's where you have the lowest temperature. And after your heat addition, that's when you have your maximum temperature. So your maximum temperature in our case, it's 1,000 Kelvin or 723, I think, Celsius, and 27 Celsius. That's going to be 3 and 1, right? So let's put down that information. My maximum temperature is T3, and in this case, it gave us that maximum temperature is, so 1,000 Kelvin. My minimum temperature is going to be equal to T1, and that is 300 Kelvin. And then we have pressures. We have pressure 1, which is 100. Is it 100? Yeah, 100 kilopascals. And we have the other pressure, which is the maximum pressure, which is 2,000. So let's draw this quickly. I have my first state here, whatever that is, and I'm going to have my isentropic compression here. And then theoretically here on a Brayton cycle, I would have this guy going straight up, straight right across the line, so there's no pressure change. And when I have my heat rejection, same thing. I have something like this, straight up, right? But in this case, we have a small deviation from the ideal case. So let's just put it down here, because we have that pressure drop happening. Okay, so we have 1, 2, 3, 4. Let's put in red what we would have in case we didn't have that pressure drop. And then this pressure here, that's 100 kilopascals, right? It's the same for both, for 1 and 4. It's not really a straight line, but straight line. Same for 1 and 4. Then for 2, that straight line down, that's a 2,000. That's a maximum one. And then the 3 is just the maximum one minus 50, because we have a 50 drop. Okay, so that means that my P2 is 2,000 kilopascals, and then my P3 is just going to be the 2,000 minus 50. Okay, that's pretty much the only thing that changes in respect to everything else we did on the Brayton cycle, right? Isentropic compression, then heat addition with a small pressure drop, Qin. Then isentropic expansion, let's work out, or work turbine, I should say. Then heat rejection from 4 to 1. And we're going this way, as per usual. Okay, so we have our Brayton cycle there. Okay, so what do we need to do? If we need to consider Cp and Cv constant, that means that our Cp for air will be 0.005 from the table, kilojoules per kilogram, and that's going to be the same throughout. And our K is just Cp over Cv, that's just going to be 1.4 throughout. Makes our lives easier. And then we have the efficiency of the compressor, which is 80%, and the efficiency of the turbine, that's 90%. Okay, so I have all the information that we need. How are we going to do this? Well, if you want to find the work output, there's two ways to find that. We can either find an area under this curve here, which is going to be the work that our compressor requires, and then we can find this area under this curve here, which is the work that the turbine outputs, and then this minus this is going to give the work output. Or we can just do how much Q in and Q out. We can get this area inside here, area inside of the cycle, which is also our work, which is just going to be the difference between Q in and Q out. Either way is fine. You're going to render the same result. How are we going to do that? Well, we have state 1 defined. It's 300 Kelvin. We need to use that to find state 2. We have state 3, that's 1,000. We use that to define state 4. So what are we going to do is, let's do the variation from 1 to 2 to find what's the ideal 2. Then we take into account that there's an 80% efficiency compressor to calculate actual 2. And we do the same thing for 3. Calculate the ideal 4 using the relationship, and then we take into account that it's a 90% efficient isentropic turbine, and we can go back and find what's the actual temperature for it. So my T2 over my T1 will be equal to my P2 over my P1, K minus 1 over K, right? And again, I'm going to stress this again just because of the your submissions. I can only use this, and I should use this, if we are considering the specific heat to be constant, right? If it's not constant, then this guy is going to change as we go from one to the other, so we cannot use 1.4, right? So that means that my T2 is going to be just my T1, it's 300. P2, that's 2,000 kilopascals. P1, that's 100 kilopascals, 0.4 over 1.4. Only unit that's left is Kelvin here, and that is 706.1 Kelvin. Okay, so what is that? That's the temperature that we would get on T2 if there were no irreversibilities in this compressor, right? So if we didn't have any increase in entropy, this is the temperature that we would get. So that's right, actually down here, reversible. Okay, but since we know that's not the case because we actually have a compressor that's 80% efficient, then we know that our compressor, we can think of it as the compressor actually going higher than it would have to, at a higher temperature than it would have to because of these reversibilities. How do we do that? Well, the efficiency of the compressor, if you guys recall, just going to be the work over the work. Which one is greater in the case of the compressor? Well, this guy's going to be greater, the actual one, right? Over the isentropic, which is just delta H of the isentropic, delta H of the actual, and delta H, because this is constant, is just going to be Cp delta T for the ideal case, Cp delta T for the actual case. My Cp's are the same, so this is just T2 ideal minus T1 over T2 actual minus T1. T2S minus T1 over T2A minus T1. So therefore, my T2A, which is the only unknown that I have, and this has all to be equal to 0.8, right? 80%. That means that 300 plus 706.1 minus 300 divided by 0.8 has to be equal to our T2 actual, which should be greater than the 706. I got 807.6 Kelvin. Okay, so it checks out. It's greater than you would need it to be, right? So what do we do now? Well, we do exactly the same process for T4, right? Because at this point in time, what we could do if we wanted to, we could calculate Q in, right? If you wanted to, because Q in is from 2 to 3, and we're going to know that that's going to be just Cp times mass times delta T, and that's going to be T3 minus T2, or T2 minus T3, right? We have T2, we have T3, you could calculate that. But let's go, before we do that, let's actually calculate our T4 so we have all the information that we need. If you guys want to take a screenshot, go for it. I'm about to change pages.
We can only do that last step when we're working with constant specific heats, right?
Can you speak a bit louder?
We can only work with that last part when we're working with constant specific heats, right?
This part here? That we're talking about?
The line just above it?
This guy? Yes, that's correct. All these. This is only when it's constant. And this guy here, it's valid for both. Okay, this is the valid for both. But this part here, when we do this transformation here, it's only when Cp is constant, right? Because the thing is,
okay, thank you.
Your entropy is going to be changing from here to here, and then if you cannot use the Cp as a constant one, you would have to take it from the tables, right? Okay, so from this part on, let's say, from this part onwards, it's only if Cp is constant Ct. Okay? All right. About to change pages. Flip pages, I should say. Okay, so let's do exactly the same process for T3 now, or actually T4, I should say, because we have T3. So, right, so T3, can you guys see it? Okay. T3 over T4 equals P3 over P4, K minus 1 over K. Okay, so therefore, T4, and don't forget, this is the reversible, right? This is, if we didn't have any reversibility, this is the T that we would get out of this. Right, so that's going to be 1,000. That's a T3 divided by pressure 3 over pressure 4. Pressure 3, 1950. Right, that's the only change that we had. Right? This is the only new thing here for you guys. So this guy renders, I got 427.9. I'll go ahead and do 428 Kelvin. This is reversible, right? If we don't have any irreversibilities. We don't have any irreversibilities in our system. But we do. And since we do exactly the same thing. What is the efficiency for the compressor? Again, it's always the one that's smaller over the one that's greater. In this case, the isentropic one is greater and the actual one is smaller. So again, Cp delta T actual over Cp delta T isentropic. And this is the change from here to here that you can only do if it's constant, right? Cp's. If Cp's are not constant, they're going to be changing. So therefore, this is equal to, wait, I changed this line. Actual one, so that's going to be T3 minus T4 actual over T3, T4 isentropic. We have this guy, 428, T3 is 1,000, and the efficiency is 90%. So the only unknown here is T4 actual. Okay, my T4 actual is 1,000 minus 0.9 times 1,000 minus the ideal one. Okay, so once again, what does this mean? It means that if I had a turbine that was 100% efficient, it would be equivalent for it as if it were able to drop to 428 Kelvin, right? And then we would get the energy from the 1000 Kelvin all the way down to 428. But since it's not ideal and it's only 90% efficient, then it's equivalent to, for me, dropping from 1000 to 885, right? So the amount of energy is not going to be the same because it's not going to be from 1000 to 430, it's going to be from 1000 to 408. Yeah, so that difference there, that boost, different boost from the 85 to the 28, that's the boost that we would get if we were able to do the reversible work. So now that we have all the temperatures already accounting for the efficiencies, we can calculate work. And there's two ways we can do that. It asks us for work per unit energy. Okay, so we can do our work output will be the work of the turbine minus the work of the compressor, right? So whatever compressor takes up minus whatever the turbine gives away. And because it's a cycle, we can also do work is also the same thing as how much energy we put in and how much energy we had to reject, right? So just like I was talking in the beginning using the diagram. So let's go ahead and I'm going to do the second one. So let's first find Q out, Q in, and find Q out, and then we can calculate what we're looking for. So my Q in, like we said, we already have the information that we need, right? It's going from 2 to 3. So we can do, restart Q in, mass, Cp delta T. I don't have mass, so just send it dividing. So I'm going to have Q in over mass. That's going to be the kilojoules per kilogram. It's just going to be Cp times the difference in temperature. That's 0.05. From 2 to 3, that's 1,000 minus 807.6 that we calculated previously, which gives me a Q in over mass of 193.4 kilojoules per kilogram. All right, so it's energy over mass because we don't have anything for the mass. And then if we want Q out, exactly the same process. Q out over mass will be Cp, but this time instead of going from 2 to 3, I'm going from 4 to 1, right? So T1 minus T4 or T4 minus T1, doesn't matter, whatever you guys find that it's easier. You can do 1 minus 4 to have a negative 1. It's up to you. Q out over M equals 0.05. T1 is 300. T4 is the actual one, 485.2. Missing out here. So this guy is 186.1. Okay, now that we have the amount that's going in, the amount that's going out, and mind you guys, it's actually losing a lot of energy in this system, right? You barely have an efficiency in this one. So the workout, it's just going to be the difference between the two. So 193 minus 186, that's about 9.3. Oh, sorry, 7.3, which is indeed little. And if we want and that's part A, right? And then if we want the thermal efficiency, you can choose what you want to do because we know we can do thermal efficiency as work over how much energy went in, which is the same thing mathematically and physically as Q out, 1 minus Q out over Q in, right? In this case, we already have the work, so let's just plug in work over how much went in. So 7.3 kilojoules per kilogram divided by 193.4 kilojoules per kilogram. Units are the same, so they go away. And we're left with 3.77, right? So it's a horrible, horrible performance out of this Brayton cycle. Expect all of you guys to do better when you go build your own cycles, right? Ever show up for these guys. So there you go. Workout per unit mass, 7.3. Thermal efficiency, 3.7%, or 3.8%, I should say.